Welcome to another video on discrete mathematics. In this video lesson, we'll discuss a problem on partially ordered sets. The problem goes on like this. We define a relation R on the set D12, which contains the set of all divisors of the number 12. The positive divisors of the number 12 are 1, 2, 3, 4, 6, and 12. And the relation R will consider all ordered pairs A, comma B whenever A divides B. Now we determine if this set D12 and this R will actually form a partially ordered set. That's question number one. We'll understand what lower bounds and upper bounds are and find the GLB and LUB of a few subsets of this set. We'll find the greatest and least elements, draw its Hasse diagram, and also represent it as a digraph. Let's get into the problem. All right. The relation contains all ordered pairs such that all ordered pairs A comma B such that A will divide B. So R will have 1, 1, 1, 2, 1, 3, 1, 4, 1, 6, and 1, 12 because 1 divides every number in this set. 2 divides 2, 4, 6, and 12. 3 divides itself, 6 and 12. 4 divides itself and 12. 6 divides itself and 12. 12 divides only itself. So 6, 4, 3, so 6 plus 4 plus 3 is 13 and 18 ordered pairs are part of this relation. And it's quite obvious that this relation is reflexive because we see 1, 1, 2, 2, 3, 3, 4, 4, 6, 6, and 12, 12. Remember that for a relation to be a partial order, it must be reflexive. It needs to be antisymmetric, not symmetric. It needs to be antisymmetric and it needs to be transitive. So we have seen that one of the three conditions is met. Let's check the other condition. Next condition we'll check is this set of antisymmetric nature. We have these ordered pairs and we'll find out if they are antisymmetric. Yes, it's quite obvious that these pairs are antisymmetric because for each pair, its symmetric opposite is absent. We have 1, 2, but we do not have 2, 1 because 2 cannot divide 1. We have 1, 4, but not 4, 1 because 4 cannot divide 1. 1, 6, but not 6, 1. 1, 12, but not 12, 1. 3, 12, but not 12, 3. 4, 12, but not 12, 4. 2, 4, but not 4, 2. 2, 6, but 6, 2 is absent. 2, 12, 12, 2 is absent. 3, 6, 6, 3 is absent. 4, 6, 6, 4 is absent. 6, 12, 12, 6 is absent. So for every element A and B, we never have both pairs AB and BA as part of the relation. Therefore, it's quite obvious that our relation R is definitely antisymmetric. Let's check the third condition next, the condition on transitive nature. For each pair, we know that if AB and BC are present in R, then the pair A, comma C must also be present in R. Looking at this, recalling this definition, let's examine the condition for various ordered pairs in this relation. We have 1, 2 and 2, 2. This must mean that 1, 2 is part of the relation. 1 divides 2, therefore it is definitely part. 1, 3 and 3, 3 will lead to the pair 1, 3, which is also part of the relation. 1, 4 and 4, 4 will mean that 1, 4 must be part of the relation. That's obvious. So these pairs have been checked. 1, 6 and 6, 6 should mean 1, 6 is part of the relation. That's true. 1, 12 and 12, 12, which means 1, 12 must be paired. 2, 4 and 4, 4 should mean that 2, 4 must be paired. We see that all of these are part of the relation. We can also check. So these are already done. 2, 6 and 6, 6 should mean that 2, comma 6, which is there. Obvious. It's a trivial check. 2, 12 and 12, 12 should mean that 2, 12 must be present. 3, 6 and 6, 6 must mean that 3, 6 should be present. We have seen that all of these pairs are present in the given relation. Similarly, 312 and 1212 should result in 312. 412 and 1212 should result in 412. 612 and 1212 should result in 612. All of these are part of the given relation. We have already checked this. Now, when we consider distinct pairs, 1, 2, and 2, 2 should mean that 1, 4 must be present. Obviously, 1 divides 4, and therefore that's part of the relation. 1, 2, and 2, 6 should mean that 1, 6 must be present, which is again part of the relation. 1, 2, and 2, 12 should mean that 1, 12 must be part of the relation, which is also verified. Similarly, combining 1, 3, and 3, 6 should result in 1, 6. 1, 3, and 3, 12 should result in 1, 12. 1, 4, and 4, 12 should result in 1, 12. 1, 6, and 6, 12 should result in 1, 12. So this completes all ordered pairs which begin with the number 1, and in each case we see that the transitive nature is clearly observed. Now let's consider pairs which begin with the number 2. 2, 4, and 4, 12 should result in 2, 12. 2 divides 12, and therefore that's part of the relation. 2, 6, and 6, 12, obviously, we have already checked this before. 2, 12 is again part of the relation. 3, 6, and 6, 12 should mean that 3, 12. 3 divides 12, and therefore this pair is also part of the given relation. We have only a few more pairs. Yes, we have exhausted all pairs here. So we see that this relation here is definitely reflexive. First condition is met, is antisymmetric, and is also transitive. So all three conditions which are to be met for the relation to be a partial order have been met by this given relation, and therefore we observe that our R is a partial order, and this combination of D12 and R is a partially ordered set. That completes subdivision 1 for us. Let's move to the second subdivision. The second subdivision wants us to identify the greatest lower bound, the least upper bound for a given subset of this partially ordered set. Now, what are lower bounds? We define this in the slide. If A, B, and C denote three elements of a partially ordered set, the element A is called the lower bound of B and C if these two ordered pairs are part of the relation AB and AC. So, for an easier way to remember, the lower bound is the number on the left. So, A is on the left, and therefore A is the lower bound of both B and C. Of course, trivially, A is the lower bound of itself because A comma A is also present in the relation due to the reflexive nature. So we can discuss this only for distinct elements. Similarly, the element C is called the upper bound of A and B. Element C is called the upper bound of A and B if we have the pairs AC and BC. So the one on the right is called the upper bound. So AC is part of the relation, BC is part of the relation. Therefore, C is the upper bound of the two elements A and B. Now, we'll use this definition and solve a problem to find the lower bounds of a subset. Consider this relation here. It contains 5 ordered pairs on the set A, which contains 3 elements. You can easily note that 2 is the lower bound for the element 0, 1 because 2, 1 and 2, 0. The number on the left is 2 and therefore 2 is the lower bound. And that's part of the, these two ordered pairs are part of the relation, therefore 2 is the lower bound. Similarly, 1 is an upper bound because we observe that 0, 1 and 2, 1 are part of the relation. 1 is an upper bound of the elements 0 and 2. So we have 0, 1 as part of the relation and 2, 1 also as part of the relation. Therefore, 1 is the upper bound of the two elements 0 and 2. Now let's discuss the idea of a least upper bound. The least upper bound is generally discussed when there are more than one upper bound elements for a subset of a partially ordered set. So consider the partially ordered set S comma R. Let's C and D denote two upper bounds of the subset Q. Then we discuss its least upper bound and greatest lower bound. So the idea of the least upper bound LUB, the greatest lower bound GLB, will actually be considered only when there is an upper bound and there is at least one upper bound. If there are no upper bounds, then there is no least upper bound. If there is at least one upper bound, then we can discuss all this. So if C and D are two upper bounds of the subset A comma B, then C is the least upper bound if C comma D. So we compare these two upper bounds and find which of them is the least or which of them is on the left. You see that C is on the left and therefore C is the least upper bound. To discuss this, we'll use an example of a relation R on the set 0, 1 through 3 containing 4 elements. We have the ordered pairs defined in the set R. It's clearly easy to identify that 2 and 3 are upper bounds of this subset 0, 1, 2 because we see 0, 2, we see 1, 2, and we see 2, 2. So 2 is definitely an upper bound because every element of this subset is related in this manner. The same can be extended to the element 3. 3 is an upper bound of this subset because we have 0, 3, we have 1, 3, and we have 2, 3. So hence, we have both 2 and 3 as upper bounds of this subset. But amongst these two, we see that 2 is the least upper bound because when we compare 2 and 3, we have 2 comma 3. 2 is on the left. 2 is the lower of these two upper bounds. And therefore, 2 is the least upper bound. Similarly, we have the concept of a greatest lower bound. Once again, the greatest lower bound is defined only when there are at least two lower bounds. If there is only one lower bound, it becomes the greatest lower bound by default. So let's discuss this. There is a partially ordered set S, and let C and D denote two lower bounds of this subset Q. And then we find out which of these is the greatest lower bound by comparing those two lower bounds. So when C and D are lower bounds, then we call D as the greatest lower bound if D is on the right. So amongst these two, D is upper, D is greater. So D is on the right, and therefore D gets called as the greatest of the all the lower bounds here. To explain this, we'll consider the same set and the relation R. We identify that 0 and 1 are lower bounds of the set 1, 2, 3 because we have 0, 1, we have 0, 2, we have 0, 3. We see that 0 is on the left. Therefore, 0 is the lower bound of the subset 1, 2, 3. And again, considering 1, we observe that there is 1, 1, there is 1, 2, there is 1, 3. 1 is on the left. Therefore, 1 is the lower bound of the set subset 1, 2, 3. 1 is a lower bound. Now, among 0 and 1, we find that 0, comma 1 is part of the set. 0, comma 1 is part of the set. So 1 is greater of the two bounds. 1 is on the right when you compare the two bounds, and therefore 1 is the greatest lower bound of this subset 1, comma 2, comma 3. So this will give us a clear idea of what are the greatest lower bound, the GLB, and the least upper bound, the LUB of a subset. Now we'll go to the problem on hand. The problem on hand wants us to find the GLB and the LUB of the subset 2, 3, 4. 2, 3, and 4 all belong to the given partially ordered set B12 because all of these numbers divide the number 12. Now we see that 1 is the lower bound of this subset because we have 1, 2, we have 1, 3, we have 1, 4. 1 is always on the left of 2, 1 is on the left of 3, 1 is on the left of 4. So 1 is the lower bound. However, we do not see any other lower bounds of this subset. There is no other number x such that x comma 2, x comma 3, and x comma 4 are part of the relation. These three ordered pairs belong to the relation only if x is equal to 1. Only if x is equal to 1, we have x2, x3, and x4. So 1 is the only lower bound. Similarly, we see that only 212, 312, and 412 are present. So the only if y is equal to 12, we find that 2y, 3y, and 4y are part of the relation. So no other number is commonly found on the right of these three elements 2, 3, and 4. So the only upper bound we have is 12, and the only lower bound we have is 1. And since they are the only lower bounds and upper bounds, we see that 1 is the greatest lower bound. So there is no comparison. The greatest, it's like that there is no other bound for comparison. Therefore, it by default becomes the greatest lower bound. 1 becomes the greatest lower bound, and 12 becomes the least upper bound. We'll consider the next subset 2, 6, and 12. This subset is interesting because it has two different lower bounds here. We identify that 1 is the lower bound because we have 1, 2, we have 1, 6, we have 1, 12. 1 is on the left of all three elements. Also, we find that 2, 2, 2, 6, and 2, 12 are part of the relation. 2 is also on the left. So, this will imply that 1 is the lower bound, and this observation will imply 2 is the lower bound. Now, there are two lower bounds. There is definitely some comparison available because there is a second lower bound available for us in this subset. So, when we compare 1 and 2, when we compare 1 and 2, we see that there is 1 comma 2 as a relation. So 2 is on the right of 1. So 2 is greater of the two lower bounds, and therefore 2 is the GLB. 2 is the greater of the two lower bounds. Now let's discuss the upper bound for this. The upper bound is quite obvious because the only number which divides all of these, two, we have, when you consider on the right, we see that there's only one number, right? 212, 612, and 1212, and 1212 as part of the relation. The only number that is on the right of all these three elements is the number 12. So 12 is the only upper bound, the only upper bound, and therefore 12 is the LUV of the subset S2. There's no other number which is the upper bound of all three elements. Therefore, it by default becomes the least upper bound. So the GLB is ready, the LUB is ready, and let's find the least element. The least element of a partially ordered set is the number x such that is the number y such that it is on the left of all elements. Here we see that 1 is the least element because we have 1, 2, 1, 3, 1, 4, 1, 6, 1, 12. All numbers have 1 on the left, and therefore 1 is the least element. Similarly, the greatest element is the number 12 because we have 112, 212, 312, 412, 612, and 1212. 12 is on the right for every element y, and 1 is on the left for every element x. So 1 is the least element, and 12 is the greatest element of this partially ordered set. Okay. The last two subdivisions of the problem are on visually representing a relation. The first of them is the digraph representation of a relation. A digraph is a visual representation of a graph of a relation where the elements of the set are nodes, points, and the ordered pairs are lines which are directed. An ordered pairs between an element and itself are indicated by loops. Checking this, we see that the digraph of our partially ordered set, which is the relation, can be done in this way. Identify that I've given every element 1, 2, 3, 4, 6, and 12 as a node, as a point. And I've represented each relation by a directed arrow mark. We have 1, 2 here, we have 1, 3 here, 1, 4 is here, drawing that, 1, 4 here, 1, 6 here. So these ordered pairs are connected and represented using directed arrow marks. Similarly, we have 2, 4, we have 2, 6, we have 2, 12, we have 3, 6, and we have 3, 12. We have 4, 12, and we have 6, 12. And there are arrows from nodes to themselves because every number divides itself. So from 1 to 1, from 2 to 2, from 3 to 3, from 4 to 4, from 6 to 6, and from 12 to 12. So this is how we express a relation as a digraph. All elements are nodes or points. Each ordered pair is a line which has a direction, and if an element is paired with itself, we express it using a loop. The next representation is exclusively for partial order, where elements once again are denoted by nodes in this representation called as a Hasse diagram. And the one relaxation is you don't have to mention directions when you represent ordered pairs. Since every partial order is reflexive in nature, loops that we saw in the previous slide need not be represented. These loops from 1 to 1 and 2 to 2 and 3 to 3, etc., need not be represented. And if we have three elements such that AB, AC are in R, but BC is not in R, then B and C are located at the same height above node A. Similarly, if A, B, C are three elements such that AB, BC, and AC are in R, then it is sufficient to represent only AB and BC because the partial order is transitive in nature. Here we express the given partial order as a Hasse diagram. So what is the difference between this and the digraph that we saw? We do not need to represent these nodes which are connected, these loops which connect a node to itself. So we don't have an arrow here, that's not necessary. And look at the strategic position of 2 and 3. 1 is related to 2, 2 to 1 is related to 3, but 2 and 3 are not related. 2 doesn't divide 3, and therefore we do not have a 2 3 pair. So they are almost on the same height above 1. Similarly, we have 2 4 and 2 6, but 4 doesn't divide 6. So 4 is almost at the same height as 6, and both are placed above 2. 6 is placed above 3 because 6 is divided by 3. 4 is placed above 2 because 4 is divided by 2. And 12 is divided by all of these. And therefore, 12 is divided. 12 is placed at the topmost. So let's find out. The pair 1 1 need not be represented because it's a loop. The pair 1 2 is here. This is the one. The pair 1 3 is here. The pair 1 4 is not necessary because of the transitive nature. There is a 1 2, there is a 2 4, and therefore this 1 4 is not necessary because all partial orders are by default transitive. So 1 3 is ready. 1 4 need not be done. 1 6 need not be done because there is a 1 2, there is a 2 6. Therefore, a 1 6 is not necessary. So this is done. This is done. And a 112 is not necessary because there is a 1 2, there is a 1 4, there is a 2 4, and there is a 1 4, and there is a 412. So a 112 need not be expressed visually. 2 2 is the loop, we don't have to do that. 2 4 is done here. 2 6 is also done here. 212 is not necessary because 2 4 is present, 412 is present. So 212 need not be drawn of the transitive nature. 3 3 is a loop that need not be done. 3 6 is here. 312 is not necessary because we have a 3 6 and we have a 612. Therefore, the 312 is not necessary. So 3 6 is there, 312 is not necessary. 4 4 is a loop, that's not necessary. 412 is here, 412 need not be done. 6 6 is the loop, you don't have to do that. 612 there is a loop, there is a edge here. And 1212 is the loop, you don't have to do this. So we observe that the Hasse diagram is a comparatively simpler representation of a partial order. The only restriction is that the relation must be a partial order, and hence, as soon as you can identify that it is a partial order, you can express it visually using a Hasse diagram. So that was this video lesson on partial orders. and various aspects of partial orders. In the next video, we'll discuss how to identify the nature of a recurrence relation and solve it using simple math techniques. Thank you.